Alright, so today we're going to be talking about heat and its relation to temperatures. So the first thing we just want to be very clear on, that temperature does not equal heat. And this is very important because, first of all, they use two different units. Temperature here uses the Kelvin scale, or degrees Celsius, or degrees Fahrenheit. Meanwhile, heat is going to be using energy in terms of joules, or calories, or capital calories. All right, and actually these are slightly different. This has a lowercase c, this has an uppercase c, and we'll explain this difference in a few minutes. And all these units right here, these are units of energy. So the temperature is a property of the system that is actually independent of the size. So if you go there and measure, 1 cup of water or 1 gallon of water, if they are the same temperature, they're the same temperature. It doesn't matter if, how large your system actually is here. So this is independent. Meanwhile, heat is very dependent on the size. So this is why if you get a drop of hot water on you, you go ow. And if you get an entire pot of hot water on you, you get serious burns. So the amount of heat is very dependent upon the size. Meanwhile, the temperature is independent of the size for these. Okay. So as for these three units up here, joules, little calories, and food calories, or the capital calories here, these are related. 1 calorie here, and this is the lowercase calorie, and this is defined to be the amount of heat, or actually I should say the amount of energy. Okay, so this is the energy which is needed to raise 1 gram of water from 14.5 to 15.5 degrees Celsius. And the reason that it's between 14.5 and 15.5 is, as we're going to be seeing later on, the specific heat of water does actually change a little bit with the temperature of the water, and it's just between these two temperatures here that you actually get what this amount actually is. If you tried it at 13 degrees, it would be very close, but it could be slightly different here. And also, this does need to be liquid water. If you're dealing with a different amount of water, this would obviously vary. And this is non-SI units, although we do still use them a lot in the States here. But if you are looking in Europe, they really don't use calories, or probably most of the world as well. They don't really use calories. They would use joules for their energy units. All right, now we mentioned here the little calorie and this capital calorie. So the capital calorie right here, which is a food calorie, this is actually equal to 1,000 little calories, or we could say 1 kilocalorie. Right. And this is what you are actually referring to, and this is why we call this food calories. So if you look on your cute little candy bar here, and if we just zoom in a little bit, when it says here how many calories this is referring to how many kilocalories. So this is, we always have to remember when we're dealing with any food items, you're actually multiplying it by 1,000 to get this this calorie definition that we have over here. So that's what we just have to be aware of, that these are food calories which are referring to these capital calories over here. All right, and then the last one we have here is a joule, and just to show what the relation is, so 1 joule, actually, yeah, 1 calorie is equal to 4.184 joules. And the joule here is one of the SI units. A joule is equal to 1 kilogram meter squared per second squared. And these are, of course, using all of the SI base units over here. So that's what an energy of the joule is. Now, as for how much this energy actually is, we can look at this in terms of either kinetic energy or potential energy as well. So, for instance, there's two terms, if you've ever had physics, you may have seen before. We have here the kinetic energy, and that's equal to 1/2 mv squared. And then there's also the gravitational potential energy, which is equal to mgh. Okay, so in both of these cases here, the m is going to be my mass, and then here this v, this is going to be my velocity. The g in this case, this is the acceleration of gravity, which is 9.8 meters per second squared. and h in this case is the height. These are all the units. So this is kinetic, this is the energy of motion. The potential energy, this is basically the energy from displacing something, moving something up or down in a gravitational field here. How can we actually figure out how much 1 joule is? Well, 1 joule, in this case, is going to be 1/2 of my mass. And just to make this fairly easy to work out, we're going to make my mass here 2 kilograms, so slightly less than a pound. So that's 2 kilograms, and then if this would be a velocity of 1 meter per second. So here, the 2 times 1/2, that just goes to 1. 1 times 1 squared is obviously just 1. So that's just going to be equal to 1 joule. So if I have a 2 kilogram mass, basically a pound, moving at 1 meter per second, which actually works out to be about 2.2 miles per hour. So just to give you a little context for that. So it's about 2 kilograms moving at 2.2 miles an hour. That has a kinetic energy of 1 joule. If we have here this 2 kilogram mass, so if I put this 2 kilogram mass in there again, multiply it by the 9.8 meters per second squared. So if I have here 1 joule would be my 2 kilogram mass times 9.8 meters per second squared times my height. So if we go here and solve this, my height works out to be 0.051 meters, which is 5.1 centimeters. So if I'm going here and raising up my 1 pound mass 5.1 centimeters, that's actually adding 1 joule of potential energy to it. And interestingly enough, since energy is conserved, if I raise that mass up, so if I take this, and this obviously is less than a pound, but if I raise this up by 5.5 centimeters and then I let it fall, its velocity actually, when it hits the ground, will be 2.2 miles an hour, ignoring effects of friction and so on. But because right here, the potential energy would get converted entirely into my kinetic energy. Now, one other thing, we're talking here about energy and stuff, but also we can just look here at something that's related to this, which is power. And power is energy divided by time. So usually the way that we see this in our everyday lives is joules, so of course our energy of joules, per time of seconds, which is what we know as a watt. We see these quite often, on your light bulbs, on your electronics, how many watts are you actually using there. So what we can actually do is relate here. If you look on any of these, food items that you buy in the store, you'll see over here basically, like how much, fat and everything this, you should have based upon a 2,000 calorie diet. So let's just say that's, about how much food energy that you should actually eat every day. And then we could actually say, well, if this is 2,000 calories and this is burned over the course of 1 day, how much power does the actual average person actually run on? Let's say I have here 2,000, and this is going to be my capital calories, because these are my food calories, per 1 day. Okay, so right here, that's energy divided by time. So what we want to do is convert this into joules per second so we can figure out how many watts, an average person runs on. So first of all, we need to convert this into my calories from up here. So remember, 1,000 little calories is 1 big calorie. So this is going to be 1,000 little calories is equal to 1 capital calorie. And then we have the other conversion up here, that 1 calorie is 4.184 joules. So that's going to be 4.184 joules per 1 little calorie. And then we have here, we have to convert days into seconds. So 1 day has 24 hours. And then 1 hour is 60 seconds times 60 minutes. That's going to be 3,600 seconds. Okay, and just to show that everything actually cancels out properly here, my capital calories go away, my little calories go away. I'm left here with joules. My days go away, my hours go away, and then I'm left here with seconds. So I have here leftover units, joules per second. So if I go through and calculate this out, what we get here is 97 joules per second, which is equal to 97 watts. Okay, so really, and since, given how many sig figs we actually have here, we can basically just call this 100 watts, and just call it a day. So essentially, on average, over the course of a day, you're basically burning as much power as an old-fashioned 100-watt incandescent light bulb. So it's actually kind of an interesting little tidbit to know there. Now, this, of course, is the average over a day. Your actual power that you give off will vary dramatically over the course of a day. Obviously, if you are sleeping, it will be much less than 100 watts, and if you are exercising heavily, it will be much greater than 100 watts. So this is just an average, for the average person, like is on here. It all depends on, your actual needs, but, average person, about that amount. The one thing that we want to talk about here, we said, temperature and heat are different things, so how are they actually related? And they are related here by this equation. Okay, so Q is equal to mc delta T. Now, what are all these symbols here? So Q is the heat, M is the mass, C is this thing called the specific heat, and the delta T here, this is going to be my change in temperature. Okay, so heat, this is obviously going to have units here in joules or calories, whatever you happen to have. It'll be obvious once we get to specific heat. The mass here, this is usually going to be units of grams. The specific heat, that can either be calories per gram degrees Celsius or joules per gram degrees Celsius. And depending on what your units are over here, will obviously determine what your units for the heat are over here. And your change in temperature, that will be degrees Celsius. It could even be Kelvin as well. As we saw earlier, the change in temperature, if you're dealing in Celsius or Kelvin, is exactly the same. Now, the specific heat, this is the big variable here that determines what your amounts actually are for the specific heat, because this depends on what substance you actually have. So here is the table from the book. Okay, so this is the table from the book here. So notice the units on all these. These are calories per gram degree Celsius for all of these. And here we have solids, liquids, and gases. So if we just look here, water has the highest specific heat of these substances, and water actually has the highest, well, one of the highest specific heats of any material. Hydrogen is actually the highest, but it's a gas and it's kind of impractical to do anything with it. But so water is, the highest one that you'll deal with on a day-to-day basis, really. Also, what's important to note here is that the specific heat is dependent not on just what it's actually made of, but also the phase it's in. So liquid water is 1 calorie per gram degree Celsius. Gaseous water, or steam, is 0.485, and ice is 0.492. So ice and steam are about half of the value as for liquid water. So the phase of your substance is very important there. And one thing that you will notice here, if you look for typical stuff that makes up like regular pots and pans, like aluminum or iron or copper, they have values which are much lower than water. Okay, and this is why if you put an empty pan on the stove and turn it on, it gets hot very, very fast. Meanwhile, you fill it up with water, it takes forever to actually heat that water up. And if you just look at these values here, so water is 1, aluminum is about 1/5 of that, iron is about 1/10 of that, copper is about 1/10 of that as well. So basically, the amount of heat that you put in will raise these temperatures 5 to 10 times faster than it will for liquid water, and that's why an empty pot will get blazingly hot very fast. And if you happen to look here at the values for gases which are in our atmosphere, nitrogen and oxygen, these are about 1/5 to 1/4 of the value for liquid water. So this is why water basically heats up much slower. And once it heats up, it holds on to its heat for a much longer time. So, in the winter, when it cools off, the air gets colder much faster. Meanwhile, the lakes stay relatively warm. And if you happen to live next to the Great Lakes, There's usually something that they refer to that in the winter, it's going to be warmer by the lake because, the lake holds on to a lot of heat. And in the springtime, it's usually cooler by the lake because the water is relatively cold because it takes a while for it to actually start warming up there. So here we have a graph of the global climate air temperature since the 1950s up until about 2012. On the x-axis we have the year, and on the y-axis we have the temperature anomaly in Fahrenheit, which is the deviation from the 1950 to 1980 temperature average. So if you're below zero, that's cooler than the average, and if you're above zero, which the vast majority of the right-hand side is, that's going to be above average. Also marked are the years when we have El Nino, which are in red and that are going to be warmer than you would have expected, and blue, which is for La Nina, which is going to be cooler than you would have expected, and gray, which is for neutral years where there is no La Nina or El Nino conditions. The part I'd like to talk about here is really the last 20 or so years. So if you look at the third red line from the right-hand side, that was El Nino in 1998. And this was actually a super El Nino and one of the strongest that we've ever seen. And we haven't seen such a strong El Nino since then, although the one in 2015 looks like it might actually rival that. If you look at the temperature anomalies since 1998, and just only that data itself, it looks like there might be a pause in the temperature increase. And there were many claims, and this is mostly from internet bloggers, not actual climate scientists, that global warming had stopped. But there are actually two reasons why this is incorrect. First of all, if you're picking 1998 as your start point, that was an anomalously hot year. So it's a bit of a cherry picking for a short period just to make the data fit their narrative. Okay, so if they happen to start in 1997 or 1998, then the temperatures start increasing again. So that's why we can't just take short time periods, because it's really just like if someone picked a few dozen days where the stock market was down and then just used that as evidence that the economy was going to completely collapse. So you have to look at the bigger story here. Okay, so the reason that the air temperatures are not increasing as much as we may have expected them to is because the air temperatures aren't the entire story. So if we take a look at the globe, you'll realize that all this blue that we have there is water, and it covers about 70% of the Earth's surface. So we have to take into account what the oceans are actually doing here. So why do we see this pause in the air temperature increase? Well, the temperature went into the water. Here we have a graph of the top 700 meters of the ocean's heat content from the mid-1950s till March of 2015. The red line is the 3-month moving average, black is the 12-month moving average, and the blue line is a 5-year moving average. Pentadal is just a fancy term for 5-year. The reason we have the average is to smooth out all the little noise due to fluctuations from the seasons and also just from the weather, so we can see the longer term trends more clearly. What is really interesting is on the y-axis. The heat content is in units of 10 to the 22nd joules. Now that's a ridiculously large amount of heat energy, and it's not something that we're used to talking about for a very good reason, because the energy that all of humanity uses in 1 year is about 6 times 10 to the 20th joules. So if we just look at the graph and we go from 10 to 16 on the y-axis, that's 100 times the energy humanity uses in 1 year. And that's being added to the ocean, in a period of just a few years. So where's all this energy actually coming from? Well, that's the sun. Carbon dioxide in the atmosphere slows down the escape of the heat from the Earth, and that heat has to go somewhere, and it ends up mostly in the ocean. And if we look at the last 20 years of this graph here, it does seem to level off a bit. So there were some worries that where is this missing heat actually going, and the answer is we need to go deeper, literally. So on this next one, we're now looking at the heat content for the top 2,000 meters of the ocean. Remember, before that was just 700 meters, so now we've gone nearly 3 times as deep. And here we can see very clearly where that heat has been going. Just for reference, that red line doesn't extend as far back because they simply just didn't have as much data back then. There weren't as many deep sea probes back then. Okay, And just to compare sets of data, here is the 5-year averages for the top 700 meters in red and the top 2,000 meters in black. And you can see that there's a large increase in heat in the oceans over the past 20 years. So even though the global air temperatures may have leveled off for a time, the total heat content of the Earth has been steadily rising. So is this a good thing? Can we just go and bury all the heat deep in the ocean? Well, no. I mean, if we look at where the heat has gone, less than 10% has warmed up, land, air, and melted the ice. So that would be, either in the Arctic or the Antarctic. Over 90% of the heat has actually gone into the oceans. So it's really the oceans which are keeping us from being even hotter than we are right now. And now, even though the oceans are storing this heat away for the time being, what can happen is a favorable wind pattern can push warm water away and bring cold, deep water up to the surface, upwelling, which can cool the air. But then that warm water is now moved deeper into the ocean, and this is what occurs during a La Nina event. However, when the wind shifts, now the warm water is being pushed up to displace the cooler water, and there isn't as much upwelling, so not as much cold, deep water reaches the surface, and warmer water from below upwells, and we get an El Nino event. And also, I should mention that the ocean temperatures, they don't equilibrate on short time scales of a few years or even a few dozen years. The oceans are really, really big, and it can take centuries to, about 1,000 years to mix all of the ocean's water. So it takes quite a while for, all that heat to get very, very deep into the oceans. So the whole point of this little interlude was to show a real-world example of how the specific heats of different materials can result in different temperature increases. The specific heat of water is 4 to 5 times greater than it is for air, and water can hold a great deal of heat. And if the heat is sequestered or released, this can cause global repercussions for global air temperatures. Also, even if the amount of heat in two different objects is the same, that does not necessarily mean that their temperatures will be the same. All right, and if we want to just use this equation up here and figure out, well, how much heat increase we can actually expect, well, let's just take off this candy bar here again. So if we have here one serving is our 230 calories. So how much will this cause an increase in temperature in, let's say, an average person if it all burned at once? Now, obviously, there's going to be some differences here because a person doesn't burn all of this at once. You have metabolism that's going to be spread out over the course of a day. But, let's just say, this is heating up an average human body size. And we're just going to figure out, how much energy or how much temperature change this actually would result in. So here I'm going to have my 230 food calories. And, of course, this is 1,000 little calories per big food calorie. And this is going to be equal to my mass, which is going to be 70 kilograms. All right, so 70 kilograms is basically an average person's mass. And then, of course, we also need to convert this into grams to make sure our units are correct. So that's going to be 10 to the third grams per kilogram. And then for water, of course, this was, as we were seeing, is equal to 1 by definition. So that's going to be 1.00 calories, little calories, per gram degrees Celsius. And then we want to figure out what our change in temperature actually is. And it works out that our change in temperature here is going to be 3.3 degrees Celsius. So if you took one serving from this candy bar and burned it and increased the 70 kilograms of water, it would actually go up by 3.3 degrees Celsius. Let's say a solid gold version of me, which would also weigh 70 kilograms, or we'll ignore the slight density differences between these. But let's just say here again our 230 calories, then our 1,000 little calories per big calorie is equal to 70 kilograms, and this time this is going to be of gold. So this is going to be of gold. And then that's going to be 10 to the third grams per kilogram. And then for gold, this is going to be 0.0305 calories per gram degree Celsius times my change in temperature. And for this case, our delta T is going to work out to be 8 degrees Celsius. Okay, so remember these are changes in temperature, not actual temperatures. So your temperature of your gold will go up by 108 degrees. Meanwhile, the same amount of water would only go up by 3.3 degrees. Okay, and that's why if you look at the little diagram we have in the book there, 1 degree Celsius temperature change for 1 gram of water for 1 calorie, that would go up by 2 degrees Celsius if you had a gram of ice, 9.3 degrees if you had a gram of iron, and 17.7 degrees if you had a gram of silver for that. Okay, and then one little final thing, and I mentioned this, in the video that we did with the temperature, that, of course, humans are very bad at measuring temperatures, and what we're actually measuring in our cases, like when we feel something that's hot or cold, we're not actually measuring the actual temperature with our physical senses here. What we're actually measuring instead is the heat flow. So it's basically how much energy is actually coming or leaving from our skin, into the surroundings, and that's what we're actually measuring there. All right. So anyway, I will stop it there.